Here, we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last two videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons, and I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation, and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to this second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges, But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases. Not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow, so instead you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with so many examples that have been labeled by humans. So a common challenge that those of you working in machine learning will be familiar with is just getting the labeled training data that you actually need, whether that's having people label tens of thousands of images or whatever other data type you might be dealing with. The hard assumption here is that you've watched part 3, giving an intuitive walkthrough of the backpropagation algorithm. Here, we get a little bit more formal and dive into the relevant calculus. It's normal for this to be at least a little confusing, so the mantra to regularly pause and ponder certainly applies as much here as anywhere else. Our main goal is to show how people in machine learning commonly think about the chain rule from calculus in the context of networks, which has kind of a different feel from how most introductory calculus courses approach the subject. For those of you uncomfortable with the relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is a L-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function like the sigmoid or a ReLU. It's actually going to make things easier for us if we give a special name to this weighted sum, like Z, with the same superscript as the relevant activations. So this is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute Z, which in turn lets us compute A, which finally, along with a constant Y, lets us compute the cost. And of course, AL minus 1 is influenced by its own weight and bias and such. But we're not going to focus on that right now. Now all of these are just numbers, right? And it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these three ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's kind of a lot of symbols, and take a moment to just make sure it's clear what they all are. Because now we're going to compute the relevant derivatives. The derivative of C with respect to AL works out to be 2 times AL minus Y. Notice, this means that its size is proportional to the difference between the network's output and the thing that we want it to be. So if that output was very different, even slight changes stand to have a big impact on the final cost function. The derivative of AL with respect to ZL is just the derivative of our sigmoid function, or whatever nonlinearity you choose to use. And the derivative of ZL with respect to WL, in this case, comes out just to be AL minus 1. Now I don't know about you, but I think it's easy to get stuck head down in the formulas without taking a moment to sit back and remind yourself of what they all actually mean. In the case of this last derivative, the amount that small nudge to the weight influenced the last layer depends on how strong the previous neuron is. Remember, this is where that neurons that fire together wire together idea comes in. And all of this is the derivative with respect to WL only of the cost for a specific single training example. Since the full cost function involves averaging together all those costs across many different training examples, its derivative requires averaging this expression that we found over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del Z del W term for a del Z del B. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of z to the previous activation, comes out to be the weight, WL. And again, even though we're not going to be able to directly influence that previous layer activation, it's helpful to keep track of, because now we can just keep iterating this same chain rule idea backwards to see how sensitive the cost function is to previous weights and previous biases. And you might think that this is an overly simple example, since all layers just have one neuron, and that things are going to get exponentially more complicated for a real network. But honestly, not that much changes when we give the layers multiple neurons. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being AL, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter K to index the layer L-1 and J to index the layer L. For the cost, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output. That is, you take a sum over ALJ minus YJ squared. Since there's a lot more weights, each one has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight matrix that I talked about in the part 1 video. Just as before, it's still nice to give a name to the relevant weighted sum, like z, so that the activation of the last layer is just your special function, like the sigmoid, applied to z. You can kind of see what I mean, right? Where all of these are essentially the same equations that we had before in the one neuron per layer case. It's just that it looks a little more complicated. And indeed, the chain rule derivative expression describing how sensitive the cost is to a specific weight looks essentially the same. I'll leave it to you to pause and think about each of those terms if you want. What does change here, though, is the derivative of the cost with respect to one of the activations in the layer L-1. In this case, the difference is that the neuron influences the cost function through multiple different paths. That is, on the one hand, it influences AL0, which plays a role in the cost function, but it also has an influence on AL1, which also plays a role in the cost function, and you have to add those up. And that, well, that's pretty much it. Once you know how sensitive the cost function is to the activations in this second to last layer, you can just repeat the process for all the weights and biases feeding into that layer. So pat yourself on the back. If all of this makes sense, you have now looked deep into the heart of backpropagation, the workhorse behind how neural networks learn. These chain rule expressions give you the derivatives that determine each component in the gradient that helps minimize the cost of the network by repeatedly stepping downhill. If you sit back and think about all that, this is a lot of layers of complexity to wrap your mind around. So don't worry if it takes time for your mind to digest it all.
이번 참조 동영상에서 우리는 backpropagation에 대해서 배웠습니다. 역전파, 5차 역전파법 또는 5차 역전파 알고리즘이라고 하는데 다층 퍼셉트론 학습에 사용되는 통계적 기법을 의미합니다. 기계학습에서 사용되는 학습 구조로 다층 퍼셉트론이 있습니다. 일반적인 다층 퍼셉트론의 형태는 입력층, 히든 레이어의 은닉층, 출력층 등으로 구성되며 각 층은 서로 교차되는 웨이트 값으로 연결되어 있습니다. 출력층에서 제시한 값에 대해서 실제 원하는 값으로 학습하는 방법으로 통계적 방법에 의한 5차 역전법을 사용합니다. 5차 역전법은 동일 입력층에 대해서 원하는 값이 출력되도록 개개의 웨이트를 조정하는 방법으로 사용되며 속도는 느리지만 안정적인 결과를 얻을 수 있는 장점이 있기 때문에 기계학습에 널리 사용되고 있습니다.